Hello, welcome to RVB Education. In this video lesson, we are going to calculate the moment of inertia and radius of gyration for an unsymmetrical I section about its principal centroidal axis. Before jumping into calculations, our first step is to test for geometric symmetry. To determine whether a lamina is symmetric about centroidal axis, we need to check whether the shape is mirror image on either side of an axis that passes through its centroid. The bounding box method is highly effective visual way to identify symmetry in complex laminas. For preparing bounding box, first identify the largest horizontal dimension. In this case, it is a 10 centimeter. Similarly, identify the largest vertical dimensions or combined dimensions to obtain the overall vertical size. In this case, 1 plus 12 plus 1 is equal to 14 centimeter. Using these overall dimensions, we prepare a rectangular box enclosing a lamina. Then, locate the centroid of the bounding box. These distances usually measured from the left edge and the bottom edge of the bounding box. Compare the lamina about the centroidal axis. We test for vertical symmetry. For that, imagine a vertical line passing through the centroid. If the left and right portions of the lamina are mirror images, the lamina is symmetric about vertical axis. Hence, the centroid coordinate lies on this axis. Similarly, now visualize the horizontal line passing through the centroid. Just see here. If the upper portion and lower portions are mirror images, the lamina is symmetric about the horizontal centroidal axis. But in this case, the top and bottom sections do not mirror each other. The shape is unsymmetric about the horizontal axis. Therefore, the centroid will shift away from the center towards the heavier side. So, we need to calculate the actual centroid mathematically using the principle of moments. Learners should note that in most cases, the symmetry of given lamina is identified by inspection only. With regular practice, you will be able to identify the symmetry of lamina quickly. The procedure outlined here is only for your conceptual understanding and is not required to include it in the solution. Next, the reference axis. If the problem statement does not specify a reference axis, it is good practice to select one that simplifies the calculation. The choice of reference axis or reference edge plays a fundamental role in centroid and moment of inertia calculations. Once the reference axis is chosen, all subsequent measurements and calculations are carried out with respect to it. Here, we choose the bottom edge as a reference axis. Now, the centroid from the bottom edge. To find the centroid from the bottom edge, let's break this unsymmetric eye section into three standard rectangles. The centroid of each rectangle component should be located with respect to chosen reference axis that make up the composite sections. Look here, centroid of eye section from a bottom edge. Here are the steps. These are the components. A represents bottom flange, B represents web, and this is a top flange. Second column represents the area of each component, and this is the centroidal distance from the bottom edge, and lastly includes product of area and centroidal distance. Then the centroid of unsymmetric eye section is calculated as, here we calculated substituting the values, and we get The value is 6.56 centimeter. The centroid of this eye section is located 6.56 centimeter from the bottom edge, which is illustrated in this diagram. Now that we have located the centroid of eye section, we calculate the moment of inertia of centroidal x-axis axis. The total moment of inertia is sum of moment of inertia of these three parts. Since the centroidal axis of entire section does not pass through the centroid of each rectangle, we apply the parallel axis theorem. We use parallel axis theorem because the centroidal axis of the individual rectangle do not coincide with the centroid of the entire eye section. The theorem allows us to transfer each rectangle's moment of inertia to the common centroidal axis before summing them to obtain the total moment of inertia. Here is the solution steps you have to see here. After solving, we get Ix moment of inertia about centroidal x-axis is equal to 900.36 centimeter raised to 4. Next, we calculate the moment of inertia about centroidal y-axis. Unlike the calculations of Ixx, the parallel axis theorem is not required for this because the centroidal y-axis of each component coincides with the centroidal y-axis of entire eye section. And this is the complete solution step by step. Just see here and we get Iyy is equal to 127 centimeter raised to 4. Now we do the calculation for radius of gyration. First, we calculate the radius of gyration about x-axis. After determining the area and moment of inertia of eye section, we calculate the radius of gyration about the x-axis. The radius of gyration is the distance from the centroidal axis at which the entire area of the section can be assumed to be concentrated without changing its the moment of inertia. Here we go step by step solution and we get the answer for radius of gyration. The radius of gyration about x-axis is calculated using this formula by including values. We get this 5.48 centimeter and which is shown diagrammatically here. Just see here. Similarly, we do this for radius of gyration about y-axis. See the steps and this is the formula. After solving, we get and this is shown diagrammatically, and with this the solution is completed. Take this problem for practice and share your answers in the comment box. I hope this video lesson helped you to understand the concept. Subscribe to my channel for more lessons. Thank you.